Okay, hello everyone, and welcome back from lunch, and welcome to ISC 25. This is our panel on quantum software for the focus area. My name is Laura Schultz. I'm from Argonne National Laboratory, and it's really a pleasure to have you all join us today. The theme this year is connecting the dots. And I'm really pleased to have this panel and bring in more highlight and more focus on quantum computing. This is a new technology that is entering into our HPC atmosphere and our ecosystem and is becoming what we hope will be another very powerful accelerator for particular types of applications and parts of applications, things that may have eluded us with the current technology that we have and that will bring us farther for discovery of science and meaningful results that have significant impact. So today I am joined by some fantastic panelists, several I have known for several years, and I'm extremely happy to have on the panel, and also some new faces that we get to learn, or I get to meet, and you get to hear more about. So I'll go ahead and introduce our panelists. Now, just for the logistics here, as you know, this is Thursday, one of the last days, so you're pretty much trained by now. We've got the microphones on the sides. Please, if you have a question, just stand up. Those of you that know me, I'm pretty laid back and informal, and we're just going to make this a really nice chat among us, and you are part of this conversation, so please just jump up, don't be shy, ask your questions. You can also ask online, and I will be monitoring this to the best of my ability. Please, I'll be looking at the chats and the questions, trying to monitor this as we go, but knowing this group and having really great conversations with them, they're very lively and gloriously opinionated, so I'm looking forward to seeing where we go with this. So I'm going to go ahead and introduce our panelists first, and with each of them, I think I'm going to introduce you as a group, and then we'll go through. You have some opening statements, very simple, who they are, kind of where they're from. I've asked each of them to wear a hat for their role as we're talking about quantum and HPC QC software. So our first panelist, our first participant today is Professor Ina Schaefer. She is the chair of testing, validation, and analysis of software-intensive systems. I love that name, at Karlsruhe Institute of Technology. We have Dr. Elizabeth Ortega here, a solutions architect at Kilimanjaro and Fresh to Kilimanjaro, so it's very cool to have you join us. We have Dr. Ariana Torres-Knoop, a lead for quantum computing at SURF, a supercomputing center, a national supercomputing center in the Netherlands. And then we have Dr. Sebastian Lang from Airbus Defense and Space. Yes, space, always in space. So, really great panelists representing different slices of our compute ecosystem, and so I think that we're going to have a really interesting conversation. So with that in mind, Ina, I will start you off to tell us who you are and kind of what you're thinking about software from your perspective.
Okay, yeah, thank you very much, Laura, for having me, for the invitation. It's my absolute pleasure to be here, and I'm a first-timer at ISC. I'm a software engineer by training. My heart is in formal methods and software correctness, and I feel software for any application doesn't have to be so bad as it is now. And I would like to open this panel with introducing to a recently funded priority program by the German Research Foundation on quantum software algorithms and systems. And for the classical computing stack, right, we pretty much know which layers of abstraction we need to make things work. We have hardware abstractions, we have operating systems, we have then connections, runtimes to HPC systems, GPUs, that kind of things. And for the quantum world, there is a pretty much emptiness on abstraction layers. I know I'm exaggerating. I'm happy to start arguing with the people who actually build solutions for quantum, but if I want to make the point and wear my hat, of course we have the quantum hardware somewhere at the bottom, and if I go to the exhibition, it seems like we can start buying the hardware soon, and then we have a handful of algorithms that we hopefully can run on those systems at some point. But in contrast to what you've seen on the previous slide, on classical computing, we are not quite there yet with what kind of abstraction layers do we need, how does it all work? So that's also a research gap, and then also something for innovation and technology transfer. So of course there are some solutions basically, or mainly vendor specific, right? So the Qiskit stack of IBM, I have Circ here on my slide. There are many, many others. There are also academic solutions like the Munich Quantum Software Stack, but we are not where we are for classical software. So the objective of the priority program and also the objective of my research is to develop and work on foundational concepts, abstraction layers, programming languages, compilers, how to actually make use of the quantum hardware that we are building, and also connect then quantum computing hardware via a very well worked out software stack to HPC, and really use classical computing, HPC and quantum in tandem for applications, and try to abstract as much as possible away from the hardware-specific things, and that will probably be something that we will also be discussing in this panel. And yeah, I think the time is now to start thinking more about quantum software to really make use of the nice new hardware.
Great, thank you. So with that, I'd like to jump then straight to the hardware. I believe that's our next slide. Yes, straight to our hardware for with Ellie.
Hi.
Yeah, it works. It works.
We change quantum stuff. So yeah, my name is Lisbeth Ortega. As a background, I'm a computational chemist, and I end up working in a vendor, quantum devices vendor. So it's a fun story. But what I want to show you, what we do in Kilimanjaro, just in a nutshell, just to know why I'm wearing this hat, is what we do. What is our oops? How go back here? So what we do, we build full-stack analog quantum computers. There is a lot of information here in that slide in one just sentence. So when I say we build, is that we manufacture. We have a team that is drawing the qubits on the paper to prepare the design, to send to manufacturer, and then measure that and check if the model is okay. And we build it from the chip to the final user. So we have this full-stack approach, where we have several layers that are coming from the case where the final user can check what we do and how they can take profit, until the chip that we have. I told that we do analog quantum computing. We do analog quantum computing. We do build chips, analog ones in superconducting qubits. But we also assemble the digital QPUs, and we are building our own simulators. So just for the one in the audience that are not so trained in what analog quantum computing it is. So just 101 here. In digital quantum computing, what we do generally is encode a problem in a circuit. And then for each qubit that we have in the circuit, we apply some modification using one qubit or two qubit gates. In analog quantum computing, here is a little bit different. I will not enter if it is better or worse or whatever, so just in the differences. Like here we encode the problem in the shape of a Hamiltonian. We set the initial state in one state that is easy to prepare, and we push the system slowly and steady until we get the final desired state that we have. And we have these two approaches, the digital and the analog one. Well, the analog isn't coming, but at least the digital one is already installed in BSc. It's a fantastic place and idyllic. So having two quantum computers inside a chapel, it's wonderful, and it's very aesthetic also. It's very, very nice. There we have these blue and red ones. That corresponds to the, to the Quantum Spain program. For now, we have these digital superconducting ones. And this project will end at the end of this year, that it will be mostly at the same moment where the EuroQCS Spain will start to be ensembled. And there we will provide our own manufactured chip, the analog superconducting one, to BSc. And we will be just besides the two quantum computers that are there. And with that, yeah, if you want to use our technology without taking to ask for resources to the Spanish government or the EuroQCS, we also have not have. We are building it now with our own quantum as a service problem. Here we have the user interface that we will have for that. It will be released in a beta version at the end of the year, mostly in November. And if any one of the audience wants to participate, we will open that. We will put it in the social networks everywhere that we are using. We are looking for users for this platform to use the digital and the analog quantum computer, just to try to fit their own use cases and try to know what we can do or we can improve when we have finally this system on the market. And during this beta access, it will be full free to use for the participants. And if you want more information about this beta access, you want to contact me, here are the details.
Okay, thank you, Ian. So the idea then, right, so we have Ina, who is working on the design of software with various parameters, the theoretical parts of moving that to applied research. We have Ellie, who is who's representing very well in particular the quantum startup environments, and of which European landscape is quite rife with, building up these systems, bringing them from physics labs environments, putting them out, getting them out into centers and into the hands of users, and then having to think about how the software is going to deliver on all of that. And then all of that coalesces into Ariana's space, where she will talk about what she does.
All right, first of all, I don't need this. I have only one slide, but I will compensate by talking, don't you worry. So my name is Ariana, I work at SURF. For those of you who do not know what SURF is, we operate the national supercomputing, but it's much more than that. So it's a collaboration for IT in education and research in the Netherlands. We have over 100 members, meaning all the universities, applied universities, research centers. They all put the resources together in SURF, and we sort of create and provide IT solutions for them. Beyond that, we're also the NRN, so that means that we manage the network between all the universities, the network between the universities and, for example, CERN. We recently had like this really amazing, 1.2 terabytes per second connection to LUMI. So we also do that. With a supercomputer, because we have so many members, that also means we have a lot of users. So more than 2,000 users of the supercomputer, which is quite a lot. And maybe more relevant here is that we are one of the last hosting sites for the Euro-HPC initiative. So we are getting, hopefully, next year, a quantum computer from Euro-HPC. Maybe just to say a little bit more about my role as a data center, I think as an HPC provider, as an HPC, when quantum computers or whenever a new technology comes out, we really start thinking, is this useful for the users? How do we integrate? What type of support do they want? Where do you want to use them? And so quantum is just like that, right? We wanted to first understand what is our role with quantum. Should we be providers? Should we be helping in this process? If so, how do we help, right? Should we try to educate? Because it's definitely different technology. So do we have a role in helping? Do we need to learn quantum computing? So if someone comes just as a normal HPC that they say, oh, my code is not working, should we then just be able to debug their codes? Because that requires a lot of expertise development within the high-performance computing centers. So a lot of these questions started arising, and we started a project about, I think, 4 or 5 years ago, where we really just started working with all the universities. So as I said, we work with universities. We have a really bubbly ecosystem in the Netherlands when it comes to quantum. Already just in the science park, which is where the quantum computer will be located, and also the data center. We have QSoft, which is one of the main algorithm developing centers. We have a lot of startups. We have the quantum application lab. So there's a lot going on. And we really rely on working on collaborations, not only internal in the Netherlands, but also externally. And I will leave it there.
Very good. Thank you. All right, so then once we've got the actual quantum systems in the data center, and we start working and hopefully have a very coherent software stack that's able to get the solution from the hardware through the system environment to the user, that is where Sebastian comes in. So can you tell us a little bit about yourself and what you're thinking about for quantum software?
Yeah, thank you for having me. My name is Sebastian Lange. I'm working at Airbus. And I'm here as a representative for the industry part. And well, a lot of people might ask, what is the industry doing with quantum computing? Of course, not much at this point. But the EU made a clever move, I think. They provided us with a research project. It's called Equality, where industry use cases are being analyzed for quantum computing. So I hope this works. Okay. So basically the main idea is there's cooperation between institutes, universities, and some industry players in order to have industry use cases in place when quantum computing finally gets on some certain stage that we can use it for our purpose. So what we have in this overall project is there are different kinds of approaches. So we have a group working on algorithms. So basically, they don't care about quantum supremacy, but transferring stuff into libraries usable for the end user. Then we have our use cases from Airbus. So this is fluid dynamics, of course, from the planes part. I'm working in the space sector, so this is what I'm going to talk about a bit. So I have a use case for data analysts for a radar satellite. So what we are doing is we have an Earth observation satellite which uses radar technology in order to take pictures of the Earth. But these pictures are in the raw data not usable. So on the upper right, you see a raw data set, which is looking like noise, white noise in the end. And you have to put a lot of effort in to transform it into a human readable image. So we actually do have a real HPC application with MPI, C++, and we are looking into ways to ease that. The complexity comes from the point that if you look at the top, you see a raw data set which provides only this single dot at the right corner there. So it comes from the type of so it would easily fill a 30-minute talk to explain how a radar technology works in that way. But in the end, what you can take from this picture is that a single dot in your human readable image will be an interference pattern in your raw data set. So this shows just the complexity of the radar processing or SAW processing. So that having in mind, we thought of where could quantum computing help here, and we have a cooperation with the University of Leiden. They suggested, okay, we might step into some processing steps and replace something by quantum computing. So the main idea is that we use a lot of interpolations, filtering, Fourier transforms, and what quantum computing might be good at is we can replace a combination of the interpolation part and the Fourier transform, which can be replaced by a non-uniform Fourier transform in the end. And this could be an entry point for quantum machine learning, because we have we found that there's a connection between parameterized quantum circuits and this kind of non-uniform Fourier transforms. So that's the basic idea of this. And I think I won't go too much into detail. So we have found various approaches we are looking into, and we'll hopefully find something valuable for the industry in the end. But having that all said, I mean, I truly believe that this will take time, of course. I mean, it's not for the industry. It's not tomorrow. It will at least take a lot of effort to be usable for us in the end. So, but I think it's a good approach that we have this quantum equality project from the EU, because we are prepared now or better prepared for the future, I think.
Great, thank you. Okay, so kind of my opening question is, I mean, this is an HPC conference. This has been the foundation of our advanced compute for several decades. We have new technologies that are coming in and taking a hold, bringing in new sorts of computational behaviors that we can add to the arsenal. But my kind of opening question is, and I'll pitch this to Ariana, as an HPC data center, what is so different about quantum in the compute, and how are we thinking about this?
Yeah, I mean, what is not different, I would say. I think there are many aspects to this. I think I already signaled to some when I was doing my opening. First of all, the expertise required as an HPC center to handle these systems is different. The type of users are different, because right now, although we obviously hope that eventually this permeates into the HPC community, right now is very much driven by, let's say, the quantum community, the quantum computing, and they have their own ways of working, right? So we need to find sort of a middle ground between them and us right now. Eventually, I hope we pull them our way. Beyond that, the infrastructure needed, right? I mean, I think a lot of you have seen a lot of the quantum computers downstairs. They're really trying to be sort of HPC ready, but it's still not something that it's, you know, as standardized as the things we have. And this comes with a lot of different complications, right? Like, how do you really integrate just in the infrastructure? Do we need to, you know, put the water cooling? Do we need to accept liquid nitrogen? Do we need to get all these things ready? Like, is it going to be feasible? Who is going to do it? So even things like that are very complicated to deal with, right? A lot of these systems are so foreign to the HPC community that we just really get a bit scared from the beginning, right? Like, what if something goes wrong? Is it going to explode? Is the helium self-contained? Like, so you really have these conversations with the data centers, right? That they're very skeptical about the whole thing, even though, you know, I don't think it's such a big deal. And obviously, from the integration perspective, it's not a GPU, right? It's really like, as we discussed before, it's more of a system-to-system integration right now, not necessarily a component, and that makes it different to other things that we normally use. So, I mean, I think I can continue saying a lot of things that are right now different, and it has to do a lot with the maturity of the technology.
Yeah, I mean, I would agree with you that it's different from a hardware perspective, right? It's a different kind of animal that probably needs different housing than other animals you have in your zoo. But I seriously hope that if we get more mature on quantum software and quantum software engineering, and if we have more integrated stacks, then from a user perspective, I at least hope, and that's the research vision that I have and that we are working for also in the priority program, that from a user perspective, that division will go away, that we will have high enough abstraction layers where we can describe problems like the one that Sebastian has in a domain-specific manner, and then that we have compilation, transpilation, transformation pipelines that to some extent can do the splitting. What do I do on a GPU? What kind of compute do I do on a QPU? What do I do classically? And then aggregate things again. Of course, I know this being a HPC conference, automatic optimization, parallelization, compilation is difficult, but at least I hope that we can raise the abstraction level a bit from what we have now, where you need a quantum software engineer and other HPC software engineers, and they are different people, and we need something more unifying, and I think an integrated software stack will be a contribution and a tool to arrive at that point.
And I think just to give a little of a baseline, so I think everyone here kind of has a fundamental understanding of what's involved with typical HPC systems. But when I first started in quantum computing several years back, you know, just the idea that there are different sorts of qubits. We are dealing with physical entities. We're dealing with synthetic qubits that you can manufacture. We're dealing with natural qubits from atoms or ions. All sorts of different beginning hardware, that we're dealing with. We're dealing with different physics that they're able to be stable longer, some of them. They're able to be truer longer than some of them. And so there's several different parameters, these animals, as Ina refers to them. On the quantum side, there's several different types and several different ways. And then you want to bring these into a system, an established HPC environment with all of the technology, the pre and post processing, the data, the networking, all of these components that we've built up and tweaked and modified over the decades. So I guess one thing is, what are some of can we kind of identify some of the hot spots between HPC and quantum in the software environment? What are some of the challenges that we're having to think about to bring these sort of technologies together?
Well, from the vendor point of view, I think that mostly all the vendors, for not saying everyone, we are following the democratization path that IBM started, that taking the user as the first thing for us. So this is why we start doing things in Python, for example, because we're very let's say, easy for the user to get started with that. Now what we are saying is, okay, we are doing all of quantum, we want to integrate in HPC, and Python is not a language for HPC, as we know. But we have, as you say, and as you say also, a zoo of different physical implementation of qubits. And we have to find all together in all the vendors, or otherwise your HPC will push it to do that. We have to find a way to consolidate our technologies together, not in the communication from the circuit to the qubit, but from the circuit to the top, to have a single layer for all of us. And if it's possible, as much as closer to HPC as possible. So this is something that we have. This is a challenge, because all of them that we have our own technology, our own qubits, our own way to communicate with them. So it's something that we cannot change, like the drivers of a GPU or whatever. But the layer that is on the top is something that we have to make big efforts, and we need centers and institutions and users.
So culture, so fundamental culture from the physics community and how they've dealt with quantum, the culture of HPC, how that translates to the languages that are used, the programming models. Ariana, you wanted to say something?
Yeah, I just wanted to highlight that right now you see a lot of quantum computing developments, but the reality is that you cannot expect as a quantum company or the quantum ecosystem that HPC adapts to that. I think quantum needs to adapt to HPC. It's a specialized accelerator, and therefore, it's not going to be pooling how HPC works. It's not. You're not going to rewrite all the software stacks, all the different things that have been done to fit quantum. Like quantum needs to figure out how to make its inclusion into the softwares as easy as possible, because otherwise it's going to be very difficult, right? And so I think this is very important, because it doesn't matter the modality. You should start thinking like not just how to give access to my specific one, but how do I enter the software stack that has been created? And there was this panel in the morning where there was a question, right? Like, okay, AI, for example, has actually been pooling how we do HPC lately. Do you think this is the same with quantum? And my answer would be no, not right now. Because first of all, we haven't proved value, so that's difficult, right? The HPC community is not going to move in that direction unless you first prove value, and it's a very specialized accelerator. And maybe here there's going to be some debate, but...
So I'm going to challenge this for 1 second. So I'd like to challenge. So I agree with you. HPC person first and foremost, I agree that quantum should be coming in as an accelerator and being added into the tribe. However, it definitely seems, and maybe this is a lesson, and this is something that some quantum companies are holding the flag for, and they understand they have to come to HPC, but there's an awful lot of quantum companies that are building from quantum first, and there's even talk about quantum first, and then it'll use the HPC when it needs it. And so there's very much this monolithic quantum solution. Also, when we hear that, when we get fault tolerant, that we pretty much don't need the HPC anymore. So I do think that there's part of a community that thinks that, that the HPC is something that you might have to deal with to get into a data center, or that may have some applicability, but, potentially the quantum could work on its own. So Ellie, as a quantum company, what would you say to that?
So as a quantum company, we know and we are pretty sure and pretty agree altogether that we will not replace HPC never. So we will coexist. And quantum has to adapt to HPC. So this is not the other way around. So we have to get a final result. So my dream is that in 2, 3, 4 years, 5, so before quantum advantage, I need to run, for example, GROMACS is a software for doing molecular dynamics, and I want to use certain subroutine for doing optimization with the analog quantum computer that we are building, that we just need to compile this software with a new flag, with the leap quantum or whatever, to have it running. So that will be the best approach to use the current and very heavy software stack that HPC has, and all the other projects related to that, like EASY, like SPAC, like EasyBuild, and so on. So we have to adapt. We have to be another player, like the GPUs.
Ina, you had Sebastian?
Well, I mean, for the sake of the argument now, I could try to disagree with them, but actually, I do agree that for me, it currently, as the state of quantum, to me, it seems like it will be just another special accelerator. So quantum should integrate into the software landscape that we have. And I mean, you were asking about challenges that I think that one of the big challenges of quantum computing in its present state, and I think that was already explained, is we are lacking interfaces, we are lacking abstraction layers, we are lacking standards or de facto standards of how quantum works, right? I mean, most vendors tend to agree that we have the gate-based computing model, but this is where I think classical computing was in the 1960s, where we're talking about gates, and since then, classical computing and HPC have evolved to like more high-level programming languages, even declarative programming languages, where we don't care about the algorithm anymore, we just describe the problem and let then tools do the work. And I think this is a challenge that we jointly, HPC and quantum, have to solve together to build abstraction layers on top of the various physical qubit realizations and sort of hardware-specific stacks to arrive at something that is more hardware agnostic, more problem and user oriented, and I think that should be a community effort to develop layers, interfaces, and arrive at standards at some point.
Thank you.
So for the HPC part, I don't think that it will be replaced by quantum. I mean, you have problems which are not better with quantum hardware in the end, and in the industry, we face always the problem that we need to adapt to a technology evolving, and it takes a lot of effort to use a new technology. For instance, it took a lot of time that the industry adapts for using GPUs really as a computing resource. So it's barely that you have enough development power to pay your employees for adapting your code all the time to new problems. And then I would say there should be a benefit behind it. So once we have quantum hardware available, it's not the purpose on having a Fourier transform, for instance, replaced by some quantum part, because it won't get better on the quantum hardware. But when we have a problem which can be solved more efficiently by some sort of accelerator, doesn't matter if it's quantum, if it's GPU, if it's an FPGA, whatever, then the industry might invest in this point now.
So where are we? Can you be just baseline? Where are we with quantum software? So, I mean, and again, we're going to talk about HPC QC integration. We're going to follow that theme. So, where are we? What is our maturation level for this sort of fluid software environment, and what are some of the biggest points, some of the sticking points that we're really working about? Ina, you've already mentioned the interfaces and standardization, obviously, but can you talk a little bit more about where those hotspots, where those interfaces exist?
I mean, where are we currently? I still feel we are in the quantum software world, if that already exists. We are like in the 1960s with classical computing, right? Mm-hmm. So before the x86 assembler arrived. So yeah, I mean, we of course we can build some examples and run some algorithms on some hardware that we can buy, or experimental hardware or academic hardware, and that runs, and we can do experiments. And currently, I mean, one of the fields that quantum computing seems to have an advantage is quantum material simulation, and there we see results that are promising. Another area where we hope that quantum will bring an advantage is combinatorial optimization, but currently the classical optimizers are so much better. And I mean, I have students working on solving traveling salesmen's problems with like 3 and 4 cities, getting noisy results, and this is getting us nowhere. Mm-hmm. So apart from the interface and programming language part, as a colleague of mine has pointed out in a stakeholder dialogue recently, we also need new algorithms. We have the handful of algorithms. A colleague of mine is joking, saying in quantum computing we have Grover, Shor, and noise. And we need other algorithms for solving problems. And then, of course, we need the hardware also to mature, to really become fault tolerant, that we can compute problems of greater sizes. So I think the development, to summarize, is both well, in very different aspects. It's the hardware abstraction layers, the programming languages, but it's also the algorithms, and it's hardware that also needs to mature more, as is it now. Mm-hmm.
Yeah, if I can add just something, this concept that someone mentioned to me before. I think one of the situations right now with the software in quantum is that we have a lot of duct tape around. So we really have a lot of ad hoc solutions, like, you know, this software does that and this one does that, so I'm just going to make this ad hoc transformation here, and then this one. And all this duct taping makes it very difficult to sort of have consistency, develop applications, right? So Ellie was mentioning the GROMACS codes, right? All these chemistry codes. Like, you want to use them to prove we can do something very cool, but then that means that you need to really sort of like duct tape from here, there, and then this output, duct tape it to that one, and then, so it's very duct taped all over the place. Obviously, there are efforts already to create a much more professional pipeline, but it's still a lot of patching.
That's a really great comment, and I do, and you know, you kind of harked to the past a little bit, because it does remind me when we think about the quantum technologies that we have right now, and we've got independent vendors who are building their hardware, but they're also building their system software, they're building their tools, their libraries, they're building the application layer, they're building the interface, you know, for their user, and we've got several of these happening in silo. This reminds me very much of early days of HPC, when the technology is up and coming, and this is also very much, as coming as a trained biologist, you know, this is very much early evolutionary theory. You know, you've got an island that becomes, you know, that comes out of the water, and you've got critters that start heading onto it. You just have this explosion of different forms, of different abilities, different forms, different functions, and all of it can kind of coexist for a bit, but then you do start having environmental pressures on it. You start having, you know, the forces that require, you know, that start to preen, that start to find the best fit for the environment and for those. So kind of in that vein, what forces are quantum technology, what are they having, what forces are happening right now in our ecosystem that is gonna cause some cohesion with these technologies and with the software environment?
That's a super interesting question. Actually, looking at it all from a biology perspective, right? I mean, in like Darwinism for quantum computing, right? So who will be the fittest to survive in that game? I think currently lots of the developments are driven by research money pouring in, or by venture capital pouring in. That people believe in like VCs believe in something and they fund startups and companies. So I think that's one of the things that push the ecosystem. Then, of course, research projects that are being run push things. So we are currently discussing about the German quantum software stack, the European quantum software stack with other universities and companies and research institutes, whether we could have some open source community effort to build standards interfaces for a quantum software stack. And I think, well, actually, we would probably need market forces stronger. If we have more applications that where companies have a win from using QC, then we will also get like that kind of business perspective push in the quantum computing community that we currently don't see that much. I mean, we have companies like Airbus and others being interested in quantum, but mainly, as far as I see it, because we are still in such an early stage, mainly companies are interested because there are publicly funded projects they can join. So I don't see a strong market push yet, but I think if we have that, then there will be other forces that will tell us which islands will come out and where will the creatures then live, to stay in your picture.
So, you want to say?
Yeah, maybe just to add up a bit from the industry perspective. I mean, we are at the end of the chain, so we will adapt something when it's very at the end of the stage, so to say. So
Matured.
When it's mature enough, because. We do not have research in that way an institute have or a university have. And from my perspective, the external forces is the most interesting part would be if we have some sort of application which is really good at quantum, then there will be an island or an evolutionary process going on, which makes this technology mature for others to be used, because we won't do it in the industry. But if we find something beyond, of course, encryption, RSA, it's the most interesting part now. But I think if there will be an evolution in some sort of, we find a killer application for quantum computing, then an island may be evolving, and then it will be usable for us.
Can I just add something? I mean,
it.
I agree. An application will be a massive force to sort of like start cohesion, good applications. Education. I think we shouldn't oversee education. Qiskit from IBM, they have, I mean, they are very successful, and in part of it is because they have educated masses in quantum computing with the software they have developed, and it's a software that was very much targeted to educate, right? And I think this is also so important, like the focus in how do we make this usable, how do we teach it? So I think if you're looking for factors on how to cohese things, it has to do also a lot with training people, right? Tutorials, how do we make this more available and reachable for people?
Now, I do have to say that being a moderator is a really challenging position for me, because I'm trying very hard not to inject my own opinions. But I hope you'll permit me one, just one. I mean, having run a quantum program and having the responsibility in a data center to bring quantum systems in, when you've got all of these different technologies and you're facing multiple silo stack solutions, for a data center, I mean, that's just untenable. We want to provide multiple different technologies, as I said before. Different sort of qubits have different sort of behaviors. We don't want to bet on any one horse at this point, and we want to make sure that we're making these available for our users. But it's also very, very hard to maintain, several different software stacks, several different systems, all of these components. And so I would challenge that one of the environmental forces is going to be the viability of these systems on the market if they want to get sold and put into centers for users. They're going to have to find some commonality. There's going to have to be some sort of merge through the software environment, in order to be able to make them marketable, that I would want to buy them and put them in the center and then have them hook up. So I think that that's a really important component, and that's what I do see. Things like some of the software environments, attacking kind of a uniform plane to bring different quantum systems into a unified software stack. I mean, that's one of the hot spots that you were mentioning. So I think that's really important. Now, we've been chatting along for a bit, and I do want to remind you, and I haven't been seeing anybody standing up, but if you have a question, a comment, please do so. And if you've heard stuff in here that you're like, that's absolutely not true, I want to say something else, then please do. This is part of your conversation as well. Yes?
You might be surprised that, please hang on. You might be surprised that I'm asking. I'm not asking as the IEC organizer. I'm asking as a KIT alumnus. This discussion reminds me to what we did at Karlsruhe more than 40 years ago. We had scalar computers, general purpose computers, and then came the age of vector computing. How to integrate vector with scalar. This was an exotic machine, the Cyber 205 in Karlsruhe. And of course, we had to deal with new programming, assembly. So it's the challenge of hardware integration, but here we are talking about software. So clearly, it's the integration into scientific applications. And I think when you use the term HPC in this panel, you think of HPC simulation software, I would say. No? Probably. No? HPC also stands for the fast computers. So we have to be very precise. But initially, I think we can learn from the experiences we did in the 80s, how to integrate vector into the infrastructure that the users were used to. No? Clearly, it was the age of batch processing and punched cards and all that stuff. But then came BLAS. We did not call an assembler call, but we had to use the BLAS language, and there was the assembly language inside. And maybe we need to define again kind of modules that are easy to use for the engineers or the scientists, and depending on the underlying hardware, the suitable code is included. Of course, the integration of quantum computers with HPC computers, so like in the LRZ, this is a different subject. But on the software layer, to make it easy, they should be able to use their existing application software and improve it or speeding up by using maybe libraries that are optimized for the given quantum computer system. That's maybe not a question, but I think it fits to your discussion. I hope maybe you can comment on that. Yeah. Thank you.
Thank you very much for the comment. I've heard those KIT alumni are everywhere. And I mean, at that point, it was still Universität Karlsruhe. At that point, and of course, it's pre my time, but I've heard those stories. And thank you very much for the analogy. That's exactly what I'm saying, that the state of quantum computing that we're at is pretty much where we were in the 80s, as you were describing. And yes, we need libraries, we need programming languages where we can fit things together. From a research perspective, I would also say that classical will drive quantum as subroutines. That is what we believe at the moment, that will be the model of integration.
Yeah, I want to add here, thank you for your comment. So as a vendor, we are keeping in mind all the history of HPC and all the history of computing. We are trying to follow the path, the successful path, because I'm sure that there will be a lot of defeats for the moment. And we are evolving on that. So for example, something that we at Kilimanjaro we consider is to have some collaboration with institutes and universities for co-design, because the chip that we are building maybe is not the most suitable chip for doing a specific problem. And if we have that feedback when we get in November our quantum as a service in the quantum computers that will be in our offices. If we have someone there that's saying, we'll need that different connectivity or that nothing, we are at the moment of the majority of the system to work in that and improve our system with this.
Yeah. Also, thank you for your comment. But I think there's a difference between the evolution of classical computers to vector machines to HPC and so on. Because the difference is, I think we now have the opportunity to understand beforehand what's going to happen. Because back in the days, it was like, there's a computer, use it for something. We don't know what to do, but it should be some value for us. Now we know what quantum computing can provide, but the technology is not there. It's not like there you have your new toy and see what you can do with it, but we can understand it in beforehand what to do. And this is a difference, and I really appreciate that we are thinking about adapting to this new technology by thinking before and not having it available and thinking afterwards what can I do with it. I mean, same is true for GPUs. I mean, the killer application was Bitcoin mining for a long time. So now it's generative AI which is pushing the industry. So it's an evolutionary process, but in this sense, I think we have an opportunity to think before we act.
Mm-hmm. I want to disagree with we know that what they can provide. I don't think we know. I mean, we have ideas, but the thing, I mean, for me, one of the biggest challenges when it comes to software integration is that there's still so much manual work. As in, we can, and I mentioned this also before in a talk, like, it's very specific problems we might be able to solve with quantum computers. Mm-hmm. And finding those problems, so it's not as simple as saying, we create a library and then just substitute your for loop with this for loop now in quantum computing. I think it's going to be still like so much problem-based, at least that's what I think. I'm happy if someone wants to challenge that. And that manual labor, I think that's one of the most difficult parts on how do you integrate it, right? Because you really need people that knows, you need the problem owners and also the people that understands what quantum computers are capable in order to figure out where you can use these routines. And I see someone is there, by the way.
Yeah, so we've got about 6 minutes left. I want to get to one other topic, but we want to definitely have a question from the audience. So go ahead, please.
Hello?
Yes.
Oh, perfect. Hi, my name is Sanket. I'm one of the hardware vendors, Qiskit, IBM, so on and so forth. I've appreciated this panel and the discussion so far. So throughout the panel, we've talked about the software stack, discovering workflows, killer applications, duct tape, what is quantum good for, what's not, right? For us, right, a majority of the researchers that we work with are focused right now on algorithm discovery, right? And we believe like the modularity enables them to do research at the levels of abstraction that they're comfortable with, as well as providing them the controls to go deeper, find more performance where they need to. So one of the things I'd like to ask is, how do you see modularity and control fitting in with this era of exploration versus what I also hear on this panel, possibly prematurely defining these very hard pipelines in this era of algorithm discovery?
Well, I have an answer. I'll take a crack at it.
Sure.
I hope that's okay. Sorry, I feel that's not my role. But I mean, that's a great question, and you definitely see there's a lot of push to understand, what you can, possibly do and theoretically do with quantum. And so there's the discovery of the algorithms and all. But I mean, I don't challenge it. I agree with it, but I offer a compliment to it that the software environment setting all of this up has a lot of machinations, has a lot of components. Sure. You've got multiple layers of scheduling, just as a disaggregated accelerator in general, but on different time scales. You've got again, we talked about the programming languages. You've got you've got the dynamicism of the compiling environment. You've got the constant changing of the quantum system that has to be accounted accounted for in the compile as it's going on. So you have all of these, components that you have to be thinking about. So you need to do this. To me, this is really a chicken and egg at the same time kind of thing. You've got to do the algorithm development and all that as you're thinking about, or as you're working on this software development. So some of it's going to be clunky, but to think about, getting the theoretically what's going to work on theoretical design constructs is not going to get you there. You've got, because you have to build all of this while you're going. So I definitely see a chicken and egg. Superposition at the same time kind of development happening. That's my take on it.
Yeah, maybe let me add a provocative hypothesis to algorithm discovery as well. I mean, from linguistics, we know that the languages that you can speak influence the way you think. And to me, it is we need better programming languages, better program abstractions to be able to discover more algorithms. And I mean, I've worked on modularity for a long while now in classical software, and I think modularity is always key. Being modular is always good to be robust against change, but and having modular language concepts where you can plug things together will help us also with algorithm discovery. And right now, thinking in gates for me is not the right abstraction layer.
Great. So I want to honor any other quick questions. If not, and sorry, this is a bit bright here. If not, we've got about 3 minutes to go, and there's several other questions I wanted to ask. I wanted to ask about the development. We talked about silos. We're trying to bring in multiple quantum systems and HPC on one side, but in a way, we're kind of siloing from what's happening in the AI community and thinking about the integration of HPC and AI. Is that different? Is it not? We're not going to have a lot of time for that question, but something for you to think about when you're over your cocktails tonight and discuss. But kind of closing with that, we've got a couple of minutes for each of the panelists. Kind of a closing thought. What do you see as, what kind of keeps you awake at night from your various perspectives of wanting to get solutions for your work, wanting to get viable systems that users use, wanting to be able to have an environment, an entire ecosystem again that the users can use using this hardware for users like this, and then bringing it all together with the design of the software environment. What's one thing that you wish we could solve immediately, that's keeping you up at night, that's something that's really a priority that we need to address as a community in the near future?
I'm going to go with the one that keeps me awake at night.
Okay, go for it.
I mean, I think it's a stage of where we are, but it's too much divergence, right? I mean, technologies, in order to develop, they need to diverge. We cannot just start converging too early, otherwise you're sort of killing the innovation. But it's really a lot, right? In all the different layers, there are different, different integration ways with HPC. There is different libraries. There is different software stacks of each company. And from a user perspective, this is going to be very difficult if you want to have the same user experience. So what keeps me awake at night is, are we going to be able to converge in a sort of like good way, right? Are we going to be able to bow to the right solutions when it comes to that, right? To recognize, hey, they did it better, let's just align to that, right? And not only here, I think in general it's difficult to do it, and if we want the users to really take advantage of it, we need to be ready to do that as well.
Okay, quickly.
Yeah, from my point of view, the thing that makes me awake at night is we are now, we'll put in the beta access of our cloud. We are building our own chips. Did we choose the correct path to do the things? Every vendor has their own way to do the things. And the one that we have to do is that, the thing is that we have the community waiting for so long that we don't want to disappoint that. So we want to have something with value, with maybe not a big system, but something that really works to let them start using that.
Okay, thank you. Ina?
What keeps me awake at night is how long the quantum hype still lasts, and if we will see a killer application for quantum before the research money runs out.
In order to get the more research money, yes. Quickly?
Yeah, quickly, just I hope that quantum computing will be not another fantasy or something which we can use in the future. I mean, and not proclaiming that everybody does quantum computing, everybody does AI, so that we have real use case in the future, like a killer application or something like that.
Okay, great. So thank you to the panelists. Kind of one final thought, and I'm hoping that as you've been sitting here listening to this, oftentimes I'm reading papers in HPC and some of the problems with AI integration or offloading it all, and I think, my goodness, I could pretty much replace the AI terms with quantum terms. There's a lot of pattern and processes that are saying there's some of the similar challenges that we have, and so as a community, there's these thematic issues that we're going to have for constantly bringing together new technologies that solve novel parts of problems in a novel way that kind of contribute to this overall whole. And I think that this theme, this mission that we have to bring up quantum systems, or quantum computing, make them viable for our user community for impactful scientific results, bringing it into the HPC fold, that all coalesces with everything that we do as a community, from the traditional mod sim, the AI, and this quantum, and that really meets and speaks to the theme of connecting the dots for this year's ISC 25. So I wish all of the practitioners in this space that are continuing on this journey great success, and I hope that we all continue to merge and work towards the future to achieve this result. So thank you very much to the panelists for your insights, your thoughts, and your perspectives, and we're slowly wrapping up ISC 25, so all the best to you, and thank you for your time. Thank you.